All right, so two announcements. So the Google Sheets schedule, I remembered as I was uploading the video to YouTube that it's sort of a pain to update that sheet because I have to upload the video, wait for the video to process, then go to it, then get the link, then copy it, then go over there. So I don't necessarily get that updated ASAP. So maybe on a weekly basis that sheet will be updated, but the videos will be on the playlist, right? So if you need to watch a video lecture, right, the spreadsheet may have last year's still, and I'll update those sort of regularly or as often as I can. But then if you need to see a particular lecture, the playlist on YouTube has all of those, right? So just because the super convenient link is missing doesn't mean that the video is not there, okay? And if I forget to upload a lecture, just shoot me an email and I'll remind me to do it. So sometimes I have meetings right after class and I'll not get around to it. The second thing is that on Friday we're going to have our first quiz, right? So it's going to start at the beginning of class, the first about 5-10 minutes. They should be really quick and easy. So does everyone here, if you don't have a cell phone or a laptop that you can access the internet, let me know and we'll figure out some sort of alternative strategy. But I'm assuming most everyone here is smartphone enabled. So I'll send out the link through Canvas. So you just got to click on the link, and then I'll open the form when I display the quiz questions, and then we can go over them if we need to, or just move on to the lecture. Okay, any questions about the format of any of those?
What's the quiz going to be on?
It'll be on what we talked about in class. So far we haven't talked about too much. So units, basically, conversions. Basic engineering stuff. Okay, so one thing that I'm going to cover right now is a useful tool. Who's used linear interpolation before? Okay, so I don't need to go over linear interpolation. All right, so one thing regarding units that I forgot to mention, most all of the formulas that you've worked with that can be solved are called polynomial functions. Who's heard of the term transcendental function? A few folks, a few of our math whizzes. So there is a class of functions called transcendental functions. These include exponent, natural log, sine, so on and so forth. Basically, the stuff you learned in Algebra 2 or pre-calculus. No units ever. So these functions don't have any physical meaning when it comes to units. So I can't take the exponent of time because that kind of botches the meaning of the time units. So anytime you see a transcendental function, you'll almost always see it, right, with some sort of a normalization to kill the units. Right? So transcendental functions, no units are produced, no units go in. So these are almost always going to be, they have to be dimensionless units, otherwise you kind of ruin the engineering knowledge behind them. But polynomials, basically anything that can be expressed as a power of x or y, those units are perfectly fine. Okay, so within the classification of units, we have base units. So this is going to be mass for SI, that's the kilogram. We have length. This is going to be meters. We have time, seconds for temperature. SI is Kelvin or Celsius. And then there are a few more examples. Electrical current is the ampere. And the last one I have down on here is a base unit that I've never used, is light intensity, is a candela. All right. All the other units that we're going to be working with are going to be combinations of the base units, right? So a joule, a newton, they're combinations of these. So in my own professional life, I have a Word document that's called units that I will refer to when I'm teaching these types of classes, where I basically rewrite all of the more complicated units like pascals or viscosity, Pascal seconds or joules or Newton meters, and I rewrite them in base units. This allows me to not have to rederive it every single time, and it helps me double check my equations. Right? My philosophy is if you don't understand the units, you don't understand the equation, you don't understand the calculation you're doing. So even when I was doing relatively advanced calculations in my graduate work, right, I was doing a technique called neutron scattering, and there was a lot of very complicated units. But every time I sort of worked through the math, I said, okay, let me work out the units, make sure everything makes sense. That they were highly complicated, and it was a very useful exercise. Okay, next we have multiple units. And this is going to be things like giga, which is 10 to the almost ninth. Then we go to mega, 10 to the 6, kilo, 10 to the 3, centa, 10 to the minus 2, milli, 10 to the minus 3. What are some other ones that we know? Micro, which is what? Okay, what else? Nano. Okay, what's nano? Okay, what's another one? Pico. Pico is what? Okay, what's the one below that? Femto.
Where do 4 and 5 go? So there's 10 to 3 is kilo, mega is 6. Where's 4 and 5?
I don't think they have fancy names. I guess engineers only like to write at most 3 digits to the left of the decimal. Okay, what's below femto?
Small.
Use a different scale.
Atto is the one below that one. What's above giga?
Tera.
Tera. What's above tera?
Peta.
What's above peta? I don't know. I forgot. I heard it recently. Oh, exo. That's what it is. Exo. Exo's above peta. All right. And I think most of you guys know these ones because of your hard drive storage space or RAM for your...
Or lack thereof.
Yeah. All right. So far, not too complicated, right? Then we have the derived units. And this is where we are going to multiply or divide our base units. So we have force, which is newtons, which can be written as a kilogram meter per second squared. Right? So when you're trying to double check and verify, converting your derived units into their base unit form is a good way to make sure that you're crossing off all of the newtons and all the kilograms and all the meters and everything like that. And then we can also just make up units as well. So another unit of force is an erg, which is equal to 1 gram centimeter per second squared. But look at the structure of it. Mass, mass, distance, distance, time squared, time squared. Right? They still have the same physical meaning, but they're just arbitrary definitions. So if you're asked to convert between length in meters to length in inches or feet, pretty straightforward, right? Google is going to be your friend. That makes it very, very trivial and convenient. However, if you need to convert between base units, that's not a simple mathematical calculation. That's actually a scientific, or more rather, a thermodynamic calculation in many regards. So, if I need to convert, for example, from mass to volume, what do we use?
Density.
Density, right? So rho is density, which is going to be kilograms per meter cubed, or using a different unit system, you can come up with different approaches. right? We could also write, for example, the specific volume which is going to be the reciprocal of the density, which is the volume per mass, totally acceptable, right? It just depends on the convention and what you want to use. Question?
So temperature current, what is voltage a measure of?
Voltage is a measure of electrical potential energy.
Is that a unit or is that
Voltage, I believe, I don't know it off the top of my head, but I do actually think it's on my document. It is some combination of these units, but I don't know what it is off the top of my head. It turns out I'm actually very bad at electrical engineering stuff.
electrical engineer?
Yeah. Well, electrochemistry is an important part of chemical engineering, and it's one that I have comforted myself in letting other people handle. Okay, so this is a thermodynamic process, thermodynamic calculation. Right? There is no right answer. The density of a fluid is a function of its temperature and its pressure. So if I'm trying to relate between temperature, pressure, and density, so I can write this like this, temperature, pressure, and more often than not, we say volume, but we could also do density as well, right? Because volume and density are just reciprocal, so that's a pretty trivial conversion. I want to have a formula that can equate between these three. What would this formula be called?
Ideal gas law?
Ideal gas law is an example. Ideal gas law is within a class of equations called, does anyone know what the formal term is? State functions are an important part of thermodynamics. They are equations of state. So in your thermodynamics class, did you guys cover the Peng-Robinson equation of state?
No.
You will next year. So the ideal gas law is a very simplified and very bad equation of state for predicting the properties of real materials. It only works for very high temperatures or very low densities. Ideal gas law does not predict the existence of a liquid. I think liquids exist. I would say the ideal gas law is not super great at predicting that. The Peng-Robinson equation of state is much more complicated. It predicts that liquids exist. And better yet, it predicts what the vapor pressure of liquids are. It predicts what the heat of vaporization is. So equations of state for converting between mass and volume, right, are necessary because this is not just a simple Google search. Now, many of you, right, may run into the situation when you're working on a project later on where you'll just say, oh, Google, what is the density of this fluid? And Google's just going to say, well, at room temperature and pressure, this is the density, right? But recall, this changes. This is a function of the state. Now, when we say state, we mean a collection of temperature, pressure, or density or specific volume, okay? So if I change any of these variables, I'm changing the density of the system. So every fluid has a density at every temperature and every pressure. Now, for most liquids, the density doesn't change that much when I increase the pressure, right? Because we model them as being incompressible, right? We can squeeze on them and their density doesn't change much. That ceases to become true once you get to several hundred or several thousand atmospheres pressure, but the temperature does influence the density quite substantially. The pressure influences the density of gases massively, right? So I can't just go to Google and say, what is the density of nitrogen gas, right? Because I need to know what is exactly the temperature and pressure of that nitrogen gas. That's where the ideal gas law comes in. Right? PV equals nRT, right? We've all seen that a million times. In my general life, I never use this form of the equation. I always use PV equals RT. What are the units of V in the way that I've drawn this equation? Because I'm going to use a lot of different nomenclatures. Yes? Volume per mole, right? And so knowing the dimensional homogeneity, we can suss out Michael's weird notation. Now, what about this one? I drew this one as a little hat, right? Because that's the thermodynamic textbook's convention that I like to follow. That usually means volume per mass, an underbar, volume per moles, right? So I may be sloppy in my notation a little bit, but if we use the dimensional homogeneity, we can suss out what I mean by these because we have to know what the units are. Question?
So thermal notation for specific and absolute and for mole is different. Between classes, or between like industries or whatever we're doing, how do we keep track of if V is specific volume or if V bar is volume per mole or specific or absolute volume or if V is I'm getting kind of
So there is no good convention. Part of this is because we have very limited accoutrements for our letters, right? So we have underbars, overbars, hats, primes, right? But we have a lot of different applications for them. Same thing with Greek letters, right? So if I went to like a collection of 100 engineers and I drew out mu, right? So if I say mu, the Greek letter mu, right? What do we think mu means?
the electric thing, the 10 to the negative second.
Oh, could be micro. Okay, what do you got here?
What?
The, what's it called, the magnetic moment.
Could be a magnetic moment.
Coefficient of friction.
Could be, okay, that's a new one to me. It's a long time since I took physics, so. Frequency. I would think viscosity would be my number one. But then also chemical potential is also given by mu. So there's no ironclad way to work this out. So the nice thing about textbooks is they should have in the opening flap usually, they usually have their notation for that particular book, right? And so when it comes to thermodynamics, when we talk about energy balances, right, is positive work into the system or is positive work out of the system, right? What was the convention you guys used in your Thermo 1 class?
Positive work
Depended on the lecture.
Yeah. And I'm equally as sloppy because I don't care, right? What I want in for those examples, you draw a diagram and you draw the arrows. If that arrow is pointing into the system, you add it. If the arrow is pointing out of the system, you minus it. And if you follow that rule, none of it matters, right? You just have to remember, I drew the arrow coming out, but it's negative. Oh, so that means I drew the arrow the wrong way. It's going into the system, right? So that's my approach on the convention. So another way that we can write this formula here is P equals rho RT, right? Still the ideal gas law. What are the units of rho that I have written there? This would be moles per meter cubed if we're following this in molar units, right? Oh my God, but I've used rho twice for mass density in this. Well, in the context, right, we may have additional information. But these are the types of questions like on a quiz or an exam. Just shoot your hand up. Did you mean these units or something like that? Very trivial questions. And if you change different industries, so if we were a mechanical engineering thermodynamics class, they don't use like the standard R, right? They use specific Rs, right, that are devoted to each different material because they do everything in mass. Right? They don't want to understand or learn the concept of a mole, which doesn't seem that complicated to me, but I'm not a mechanical engineer, right? For R, what units of R do you guys like to use? Now, there's one that in chemistry that everyone likes to use, but what do you like to use in engineering?
I've never learned the units of R.
Oh, wow. It's like one of the only things that I actually remember.
We're just given a number. Sometimes we give units with it. I've never been good with it.
Kilojoules per kilogram Kelvin.
Kilojoules per kilogram Kelvin. So
Kelvin. Depends on the problem.
kilojoules per kilomole Kelvin, you mean, right? Okay, so what would that number be?
8.314.
8.314 joules per mole Kelvin, which is equal to meters cubed Pascal per mole Kelvin. That's all I ever remember. But converting these is pretty straightforward, okay? So the ideal gas law is an equation of state that is necessary to perform these thermodynamic calculations to convert between things that are as simple, we think, as between mass and volume. Not something we can just type into Google and have Google tell us what is the density of argon. That doesn't make any sense. Google is not a trained chemical engineer, right? So Google will maybe give you a table of the densities. Why would you even bother doing that, right? That's why we have equations of state. Now, when we have to do more complicated calculations, so for example, if it's not an ideal gas, what if it's a non-ideal gas? How do we accurately estimate the density, right? So let's say, for example, I'm building a chemical reactor. Now, the thing we have to keep in mind, all right, so many of you, I'm sure, have driven past North Salt Lake and you see all the refineries. Are they big or small?
Relatively small.
According to Marathon, they're small.
Marathon, well, so they're decent size, right? I mean, they're all around like 100,000. I mean, the big ones are around 100,000 barrels a day, right? The biggest refineries in the world are on the order of 500 to 700,000 barrels a day, right? So I don't know, many of you probably don't own a home, but if you ever like purchased things, it's expensive, okay?
Yeah.
If I'm building a reactor, these reactors are the sizes of houses or even like small buildings. They're expensive, right? So if we want to know that we need to get this volumetric flow rate pumping through that system, we don't want to use the ideal gas law. Because if we botch the density of this material or the pressure of this material, you're going to have an explosion, you're going to have to replace the equipment, or you're going to have a lower throughput in your process, right? So this is why chemical engineers care about the ultimate pedantic type calculations, because a small fraction of a percentage mistake could cost millions and millions of dollars. That's why we spend so much time worrying about the density of a prediction of an equation of state for, right, a given temperature and pressure, right, to give us some context of that. Specific gravity, are we all good in that concept? So if I say SG is 1, what does that mean? Okay, no, so we'll do that one here. Well, so they did a really good job in a lot of the introductory stuff, so it's hard to know. So SG is equal to specific gravity. Ugh, specific. So an SG equals 1 is equal to 1 kilogram per liter, 1 centimeter, 1 gram per centimeter cubed, or 1,000 kilograms per cubic meter, right? So this is the density of water at STP. So what this is, the specific gravity is the density that we care about divided by the density of water at standard temperature and pressure, which is 1 atmosphere and 25 degrees C. So it's a really convenient way to communicate what the density is without having to give you the units. Right? So for example, solid lead has an SG of 11.34, which means that its density is 11.34 kilograms per liter. Okay? Which is a convenient way to communicate these physical property information. All right, so chemical engineering processes, as we discussed last time, operate 24/7 at ideally the perfect conditions, right? And what we define as the perfect conditions are the ones that maximize the efficiency of the process. So we get the most product formed at the ideal purity. Now that's not maximum purity, that is the purity of the product specifications, no more, no less, right? Using the minimum amount of money, using the minimum amount of electricity and energy, right, to maximize the profits. So this is one area which is very nice because generally saving energy makes money, right? So it's not necessarily having to be a competing effect. Now with environmental regulations, that's not necessarily always the thing, but environmental regulations are going to be additional constraints to consider. Now, because this is operating 24/7, most of the problems that we're going to be working with are going to be used solving open, steady state problems. Right? Who knows what those terms mean? Okay, a few folks. So what we mean by open and steady state is that we're going to have some box as a process. Open, meaning mass enters and leaves the system. The term steady state. Okay, who knows what steady state means? What does it mean?
No accumulation.
No accumulation. So what this basically means is that the derivative of any variable of the system with respect to time is equal to 0. Right? So that means, what is x? X is everything. The temperature doesn't change as a function of time. The pressure doesn't change with a function of time. The mass of the system doesn't change with respect to time. The volume of the system doesn't change with respect to time. The energy of the system doesn't change with respect to time. The entropy of the system doesn't change with respect to time. So the only way that I can attain steady state is if the mass entering the system exactly equals the mass out of the system. Otherwise, we have an accumulation, and the pressure either goes up or the pressure either goes down. Right? Now, in the real world, this is impossible to maintain perfectly. But there is a class in your senior year that is designed to try and reach this standard. Do you guys know what that class is called? Process control. Right? These chemical plants are so complicated that we basically have to build specialized machines that tell us how to turn the knobs in just the right fashion to make sure everything is stable. So back in the day when I graduated, right, we had a 3-story distillation column in the senior projects lab. And so we would be on walkie-talkies, right? Because in the basement, that's where you had the reboiler of the distillation column, and you could control how much steam was going in and out of the reboiler to figure out how much energy you were pumping in. At the top of the column, you had a cooling coil for a condenser to figure out how much you're cooling down the top stream. And we would be on walkie-talkies trying to get this thing to level off to steady state equilibrium. And it's extremely hard, if not impossible, for humans to do it, right, manually. So that's why we have to have control systems that are more precise, more careful, online monitoring, automated valves, all those different things. So much of the senior year is designed to apply the principles that we're going to cover in this class, how to actually make it work. Yes?
Why did we get rid of the distillation column?
It was very leaky and disgusting and old and sort of starting to be a health hazard. It was just filled with isopropyl alcohol and water, so it wasn't like, you know, the most catastrophic materials in the world, but it was like from the 50s. It was an old unit op that Chevron, I think, actually had in one of their, in their refinery, and that they donated, but it was from the 50s, and so it was like 60 years old by the time I was playing with it, and so they figured it was probably best to just get rid of it and not bother maintaining it. I don't think we lost a lot by not having it there, though. It looked really cool, right? And you had those grates where you could see down like 4 floors, so that was always fun. Okay, so we're going to mostly deal with open systems in the class. So as a general rule, if you see a problem and it's not obviously a batch system, you're going to assume it's open and steady state. Now, at the end of the class, we're going to talk about non-steady state processes, right? And that's going to be involving systems of ordinary differential equations. So it's not too bad, right? We'll sort of demystify differential equations a little bit. But the notation for flow rates is we're just going to put a little dot on top of everyone's heads. So m dot is kilograms per second, or pounds per second, or minutes, or sorry, like grams per hour, right? Just any unit of mass flow rate divided by time. Likewise, V dot is going to be equal to the volumetric flow rate. The key thing to remember is that it doesn't necessarily really matter because the seconds are on all the variables. So everything works out as if it was almost just like a closed system to many extents. So then we can just get the density, for example, right, as the mass flow rate divided by the volumetric flow rate, because the seconds just cancel out, right? Kilograms per second, meters cubed per second, and that just gives us kilograms per meter cubed, right? So the flow rate scenario is not necessarily going to be something that we have to be scared of, right? All right, so we're going to use units to help us solve a problem. Can be anything. Could be minutes, could be hours, could be years, right? So for example, if you're trying to figure out the profitability of a chemical process, right, you need to make 1 million tons of this material a year. So your time units may be per year, right? How much raw materials do you need to purchase if you can convert 40% of your feedstock into the chemical itself?
I was meaning in like dot notation. Is dot notation always mean seconds, or can that?
No, it's any unit of time. So the dot notation here, for example, this is going to be some volume unit divided by some time unit.
Will that be given in like exams?
It could be something you're given, it could be something you're solving for. Right? So the key thing with this class is going to be that we're going to talk about the system of having to do these calculations, but there's not going to be one universal rule that we're always going to follow. Right? So at the end of basically the second week of the class, we're going to have a series of tools, right, where we can derive maybe 3 to 4 to 5 equations for any particular problem. But it's not going to be obvious that you always substitute equation 1 into 2, equation 2 into 3, equation 3 into 4, and you solve the system. Right? You're going to have a system of, let's say, 3 equations, and you're going to have 3 unknowns. And you're just going to have to figure it out. Right? So there's going to be no universal system, and that's going to be the challenging part. It's not like when you get this problem, here's how you solve it, apply this algorithm. The algorithm is going to be you becoming better problem solvers. And so that's why this one's kind of the first sort of fun engineering class. All right, so let's just look at a simple example here of a nozzle. So we've got some cross-sectional area of material coming into the system and a smaller cross-sectional area coming out of the system. Right? So we're going to say that this area here is 1 square foot, and down here is going to be 0.1 square feet. The velocity going into the system, right, and the velocity coming out of the system. If we say that the velocity in is equal to 1 foot per second, what is the velocity out of the system? So take a moment. This can be solved just by inspecting the units, and we're actually secretly doing our first mass balance, right? So we're going to assume that this is a steady state open process, so we have no accumulation of mass, so all the mass coming in is equal to the mass coming out. And we're going to make one other simplification. We're going to assume that this is what we call an incompressible fluid. And what we mean by that is that the density is not a function of the pressure. So if I squeeze this fluid, its density stays the same. And this is generally a very good approximation for liquid. So if we assume that this is water, that basically means that the density in is going to be the same thing as the density out. All right, so let's just use our units and figure this out. Oh, sorry, this is 1 cubic foot per second, not 1 foot per second. Do you have a question?
Actually, is this assuming that it's incompressible?
Yes, so we're assuming that the liquid is incompressible, which means that its density is not changing as a function of pressure. So if the pressure changes in this nozzle, we're going to say that the density stays the same. So using only the units, we know nothing about the fluid mechanics of this. We just can sort of suss out what we expect the velocity to be. Sorry, I totally set this up because I botched my units. I want the velocity out. But we also don't know the volume out. Sorry, I confused myself. So this is the volumetric flow rate in. I confused myself because I forgot to put the volumetric flow rates. The volumetric flow rate in is 1 cubic foot per second. We don't necessarily know what the volume out is, but if it's open and steady state and incompressible, it should be the same. I want to know what is the velocity out and the velocity in. Right, so this is going to be some unknown in feet per second. But I confused myself because I forgot to put the cubic feet per second here. So first step to give everyone a bump in the right direction, how can we get velocity in feet per second from the units that we know, cross-sectional area and the volumetric flow rate?
Just divide volume metric or flow rate by the area.
Yeah, so I'll do little v here to make it as confusing as possible for velocity, right? This is going to be feet per second, right, which we can get feet cubed per second divided by feet squared, and that gives us the right units. So that's then going to be the volumetric flow rate divided by the cross-sectional area, right? To a first approximation, because we don't know all the physics necessarily, but this is what we do in the fluid mechanics anyway for an incompressible system. Who has the velocity out? Okay, a few folks. So let's walk through the next step. So in this case here, the mass flow rate in has to be equal to the mass flow rate out. So I want to relate this to the volumetric flow rate, right? So mass is equal to kilograms. The density is kilograms per meter cubed. So how can I get this in terms of volumes? I just have to divide my mass by the density, right? So if I do mass divided by the density, right, then that gives me kilograms divided by kilograms per meter cubed, and that gives me the volumetric flow rate, which gives me units of meters cubed, or in this case, feet cubed. So then if I take my mass balance, all the mass coming in is equal to the mass coming out. I divide both sides by the density. So this would give me mass in over density is equal to the volume in, which is equal to the volume out, which is equal to the mass out over the density, right? Because the density is constant for this system. Yes?
And we're assuming that the density is constant because it's incompressible?
Correct. If this was a real world system, not necessarily. For a liquid, yes. For a gas, no. Right? We wouldn't necessarily assume that this is incompressible. But even for a lot of aerospace engineering calculations, we assume that air is incompressible also. So for airplane wings and things like that, unless you're going close to supersonic speeds. Yes?
V dot denotes a flow rate.
Yes.
Right? So where did the second, per time go?
It's still here. I just sort of didn't bother with it. So if I just add this per second, and then it'll pop up over here per second, right? Yes?
So these kind of incompressible fluid assumptions aren't uncommon in real world problems?
Correct. For liquids, they're extremely common. Because unless you're doing something at several thousand atmospheres, it's a pretty good approximation. All right, so now we know what the inlet flow rate is, right? 1 cubic feet We can calculate its velocity in, which is just going to be 1 foot per second, right? Because it's 1 cubic feet squared divided by 1 square foot. So the velocity in is just equal to 1 foot per second. And the velocity out is going to be the same volumetric flow rate, but divided by a smaller cross-sectional area. So the velocity out is equal to 10 feet per second. Right, so just playing with the units, we can do a lot of damage. So the units are very, very powerful for engineering calculations. Okay, so the last little bit that I'm going to cover is maybe a review or a recap, but it just sort of closes out what we're talking about in terms of units and conversions. So I don't think, do you have to go over, you guys have heard of pound moles?
What?
Or moles? Okay, so we've got, now pound moles is something that I never work in, but it's something that the world oftentimes will throw at me. So molecular weight converts between mass and moles. Right, so I'm thinking of a lot of these calculations as just fancy conversion factors, right? Because I think if we know how to do the conversion factors, it's pretty easy to process the input and the output variables. So for water, this is approximately, and I'm just truncating at the decimal point, 18 grams per mole. We can write this as 18 kilograms per kilomole. Right, just times the top and bottom by 1,000. And then the unpleasant one here is 18 pounds mass per pound mole. So what a pound mole is just a different number of particles. Right, so Avogadro's number is 6.022 times 10 to the 23. Avogadro's number is different if we're using the units of pound moles. But I wouldn't stress about committing this to memory. For the most of your professional life, you will have access to Google. So if you run into this, you can just type in pound moles into Google, and you can refresh your memory. Right? So it's just basically an annoying way to communicate the quantity of material as a pound mole. So if we looked at the average, sometimes this is helpful. The average molecular weight, the notation that I'll oftentimes use is just put the bar over the top, indicating that it's an average. This is going to be equal to the mole fraction multiplied by the molecular weight of that individual species, where x of I is equal to the mole fraction, which is equal to the number of moles of species I divided by the summation of all of the moles in the system. Right? We can also write this as n of I over big N. So this is number of I divided by total number of moles in the system. Yes?
So since for pound moles, the value is the same, the units are slightly different, would it be safe, would it be a bad idea to just pretend it's a nice unit if you're using an equation?
So pound moles are useful if you don't want to convert from engineering to SI units. But for most all the examples in class, I'm just going to do SI.
Wait,
so
engineering not in SI units? Is engineering like not in
American engineering units. So pounds, pounds force, BTUs, right? All those different things. I work almost exclusively in SI. And I just think this is just an inconvenience, right? So worst case scenario, let's say you go out in the real world and like you're forced to use American engineering units. It's like 30 seconds of work just to convert everything to SI. Does that make sense? That's my approach. Okay, mole fraction. That make sense? So mole fraction is something we made up, right? It's just a useful thing for us to make up. So there's a condition that you must satisfy for mole fractions, and that's the summation of all the mole fractions have to equal to 1, right? And that's going to be a useful tool that we're going to use, right? So this is a consistency relationship. Consistency of mole fraction. Now, in the notation that we're going to be developing as we go out through the classes, oftentimes we'll write mass fraction as x, sometimes we'll write mole fraction as y. When we get to two-phase systems for liquid and vapor, the vapor mole fraction is going to be y, and the liquid mole fraction is going to be x, right? But we only have so many letters that we'd like to use, right? So the key thing is context, right? So just because it's x here doesn't mean it always has to be x, right? We can use any variables we want. We just need to be clear and consistent about what representations we're doing. Does that make sense? All right. One more series of units for concentrations. So units of concentration, one way that I can think about this is I'm converting between number of one species, let's say number, let's say amount, to the total amount. Right? So if I say it's like the mole fraction is 0.1 of species A, right? I'm relating how much of A there is in the system to the total amount of the system, right? So if I know that I have 1 mole of A and its mole fraction is 0.1, then we can suss out that the total amount of moles in the system is 10, right? So I'm converting between the concentration of one species to the total amount in that particular stream. So we also have units of molarity. What is molarity from your chemistry class? Moles per liter. Okay, we have molality, I think, is moles per kilogram, right? We also have units of ppm of I, which is equal to parts per million. Okay? So things like ppm and ppb, which is parts per billion, and ppt, which is parts per trillion, these oftentimes come up in water quality and environmental issues. So if any of you get a water bill, every year you'll get a report from the county that basically says how much arsenic and lead and all these other different dissolved materials are in the water, and they're generally reported in parts per billion or parts per trillion. Yes?
Is that like per like 1 atom of lead for 1 atom of water, or is that by mass? Like what's the part?
You wish it was simple, right? It's not. So, parts per million is going to be written as, for example, yi times 10 to the 6, right? Parts per billion is going to be yi times 10 to the 9. So is y mass fraction or mole fraction? Which one is it? Well, it depends on the convention. So for liquids and solids, this is generally going to be based on the mass fraction. For gases, it's generally going to be based on the mole fraction. So it's not necessarily one atom or one molecule compared to all the other molecules, except by convention where it happens to be in gases. But in liquids, it's generally going to be the mass fraction. And this is where just asking clarification questions makes things a lot easier. But this is the general rule that parts per million and parts per billion are going to do. It's just taking the mole fraction, the mass fraction, and scaling it. One thing you'll notice is that engineers don't like looking at ugly numbers. We'd like our numbers to be right around 1, right? And my recommendation, and I'll have a lot of recommendations for computational calculations, make the computer do the work for you, right? So if you have a spreadsheet and the output answer is 0.00073 and you're trying to compare it to another number that's 0.0065, right? Your brain goes 0.123 O's, 0.123 O's. You just wasted like 10 seconds of your life that you'll never get back. But instead, have the computer put it in units that are useful, and then you can be like, oh, 7 and 6, different numbers, great, right? Super quick like that. All right, so quiz, next lecture, start a class. You're going to get an email with a link, right? If you miss the first 10 minutes of class, you're out of luck. Oh, one last thing. Rashmi, I totally forgot to introduce you. You didn't have to stay for the whole class. Rashmi is our TA for this semester. So Rashmi, if you want to stand and wave. Hi, Rashmi. Hello. So Rashmi is going to be a very good resource if you want one-on-one time and assistance, right? So I'm going to host office hours that are going to be more focused on solving the homework problems, right? But Rashmi is going to be perfect if you want a little extra assistance to kind of go back over old materials, exam prep, things like that. All right, see y'all later.